That usually helps.
Usually.
Screen. How you doing, Mike?
Oh, okay. How about you?
Good. We need one more person here. We always need five students so that I can make this a larger window. Drives me up a freaking wall. First thing, let's go to, where's my mail? Okay, Mike, you sent it in. How'd you do on it?
We're soon about to find out.
I know the first one was Jim. You turned it in. There we go. So let's take a look at yours. The reason I do this is your neatness is just really easy to follow. So the first one is problem 7.18. So again, look at, just so you guys know, look at the way he does this. So like, given the locomotive is this much mass, the velocity, the location, right? So the motion is this way, the Coriolis force to the right. I like that you do these diagrams just so that you're clear on what you're looking for. So we're going to figure out what the force is, which we know the acceleration is 2 omega sine phi times v times the mass. You put this in, you get 79.57 newtons. Okay, that's pretty straightforward. Then you have this, right? You're at 40 degrees north, that you have the spacing of the contours, you have the distance. Now, Nick, this wasn't the one you're dealing with the ships, right?
Yeah.
Okay. So from the geostrophic equation, right, we have the geostrophic wind is 1 over the Coriolis parameter, F, which is the change in the geopotential over the distance. This is in natural coordinates. Okay, so, and again, the negative signs disappear in the y direction. You just want to be careful, and you can always interpret it based on information and what you're trying to get. So simply you plug all these things in there. Wind is from the west, low pressure is to the north, following the Weiss ballot of 2.1 meters per second. Is that what you got, Nick, Mike?
No.
I got something like 20 meters per second.
Yeah, like 20.
20.1.
Oh,
Let's see. See, on this thing, right, you probably go, see, what I would probably do here is I would just write the equation 60 divided by, like here, I would do this.
oh.
I mean, whoop. I would do d phi dn equals 6.0 times 10 to the first meters per 3.0 times 10 squared times 10 to the third, which is equal to 6 times 10 to the first meters divided by 3 times 10 to the fifth meters. And you do have 2 times 10 to the minus fourth. So, okay, so that's right. Did you guys get that?
2 point. Oh, for the geopotential.
Yeah. So, I mean, it's this kind of stuff. One of the rules, Jim, and when I do my intro class, is I always say write everything down, all the given in scientific notation. And then that will clear up any possible mistakes. The meters do cancel, so you're getting that right.
Yeah, that looks right. I just plugged it in as
what's missing? I see what's missing.
gravity.
Right?
Mm-hmm.
I think you need to have gravity in there. which will give you basically a factor of 10.
Yep.
So that's all you missed, right? So for me, if I were grading this, in a specific class, I would just go, oh, that's just one little mistake. That's really not that big of a deal. But the process is so good. Those of you who go into Northern or wherever you're going to school, when you do this, they're going to be a little bit more particular and they'll take off points. But given the fact that there's so much neatness to this, the teacher is probably inclined not to take off too many. So the only difference here is you would have to say, well, it's probably just the fact that I've got the gravity would have been wrong in here. So I should have that in there. Okay, let's skip this one for a second. What's the last problem, or is it just those? No. How'd you do on this problem, guys? Were you able to do that?
Mm-hmm.
Nick, I didn't see your mic. How about you? Jacob, I haven't seen anything from you all semester. Did you do it?
Yeah, bad news. My computer died last week, so
Okay, so
lost a bunch of stuff.
there's
Hopefully
the
I'll get it back
condition.
at the end of the week, but otherwise I'm gonna have to redo a bunch of stuff.
Is there any way to fix that?
Hopefully.
I mean, not fix the computer, but actually save the stuff?
I won't know until the end of the week when I get it back if it all survived, because the battery died, and I don't know if the hard drive is still intact.
Hard drive should be intact if the battery just died.
Yeah, they should be able to save your hard drive. That's pretty straightforward.
They can pull the hard drive and put it in a mount. You can plug it in on your USB.
Do any of you guys have those external hard drives?
Yes.
Yep.
Yeah, they're nice to have. I've got a bunch of old computers. I don't know what to do with it. I have so much information. I don't know how to go get it all. But if ever I was desperate for something, I would have it. So, and they're pretty cheap. You can run a hard drive externally. So, anyway, so the gradient wind, blah blah blah. We have the quadratic formula. Now we start to make solutions. So real solutions exist if b squared is greater than 4ac, or minus 4ac is greater than 0, or b squared is greater than 4ac. So he puts that into the equation, and that's what we end up getting. So this is just really pretty much putting out the gradient wind equation, the quadratic formula, and solving for what you need to know. Nick, where's yours, buddy? Did you do yours here?
Yeah, I swear I sent them to your email.
No.
Awful.
I know you did. And you did all 4 of them, right?
Yeah.
I got yours last night. I know, here it is.
Yeah, with the first problem, I guess I just took the completely wrong approach to it. But the other 3
Right.
were fine. So.
Yeah, so b squared minus 4ac must be greater than 0.
Mm-hmm.
So in here, you're just going to say 2 omega sine phi squared. Yeah, what I would say to you, Nick, is that you might just want to be a little bit more specific. I mean, not specific, just maybe just a little bit more ordered. Separate some of this stuff out, isolate it. You know what I'm saying?
Yeah.
Obviously, this reflects what's going on in your mind, and your mind's getting it, but it's just a little bit disordered, and it might serve you better if you try a little bit better.
Yeah,
but,
I can see here.
But you plug this in here, bring that over to the other side, and then you're saying this is f squared, which has to be greater than or equal to this. You divide, you multiply through by RT, divide by 4, and you're getting that over this gradient, so that you can actually see what is the gradient based on the Coriolis parameter and the radius of trajectory. So in here, and this is just to kind of refresh what we talked about, I want you to think about this as a teeter-totter, right? We have a balance of some sort. So on this side of the balance, you've got the terms F. Even though it's F squared, I don't care about that. You have RT. And over here, you have the, well, I'm just going to say the pressure gradient, okay? And what I'm saying is that this is the only thing that can be balanced by those two. So if the pressure gradient force gets larger, what has to happen to this side? Well, the first thing that you could look at is that this would get larger. But is that realistic? Is there anything in here that's actually a variable? And that's a weird question to ask you. Do you understand what I'm trying to say? Is there anything here that is truly a variable? Are you guys there?
Yep, we're here.
Did I share my screen?
No, you didn't.
Oh. Well, are you serious? Oh, this whole time I've been showing you, pointing and drawing pictures?
Yes.
You've just been listening to me like I'm Magic Man talking. I thought I did share my screen.
Figure out what we do.
You turned it off.
Oh, it turned off. Well, why didn't you tell me it turned it off? All of a sudden you disappeared. I'm like, where are you guys? Okay, where did I turn it off? Did I show you the teeter-totter?
No.
No.
Okay. This is what I mean by a balance, a teeter-totter, okay?
Okay.
I like to use teeter-totters as equations, okay? So what I'm saying is I have this equation on the teeter-totter, okay? And I've got F on this side, and I don't care that it's F squared. We know that the variable is F. We know that RT is there, the radius of trajectory. And then this is basically the pressure gradient force. Here they're using the geopotential. You could use geopotential height. You could use pressure gradient, whatever you wanted to use. It's the pressure gradient force. So I said, okay, what is F? Is this really a variable?
Not really.
Why not?
Well, you got 2. Omega is a 2 is a constant. Omega is a constant.
Correct.
Theta
Phi.
or phi is not really, because it's fixed at that location.
Yes, okay, that's exactly right. So you've got your latitude, which is truly a variable, right? I can set up wind systems anywhere on the planet, closer to the North Pole, closer to the equator. It doesn't really matter. But when I'm doing a problem and I'm looking at the wind solution at a location, it's not like I can just change the latitude. The latitude is sort of like saying, what's the wind doing right here? So this one doesn't really become a variable. So the only variable says, if this becomes larger, then what will the radius of trajectory have to be? It has to become larger also, which means it will not be a tight curve, right? This is the radius of trajectory there. If it needs to be larger, then the curve is going to be not as sharp. You're not going to make the strong curve.
Maybe lobe.
And that's what we're saying, is that if the pressure gradient force gets too strong, the air can't make the curve. Now, I want to show you something just to give you an analogy of this. Imagine that I've got a road and I'm banking the road. So I'm going in a curve. I'm going around a curve on a highway. What I want to do is I want to bank the curve, because basically what I'm saying is, for a car that's here, there will be a force pointing this way. That's the centripetal force. But the experience of it is the centrifugal force, right? It's like you're centrifuging. You're being pushed into it. So this is really what's going on, is that you've got the centrifugal force. Now, with respect, so you need to kind of like turn your head with respect to the road. There is a component of this force that's going off the road on the outer banks. And then there is a component of the force pushing down against the road. Right? So the car is going around this curve. There's an outward force this way. That outward force is this blue force. Maybe it would have been better if I drew blue, but it's this outward force. There's a component pushing up. So what actual force is acting on this? Like what real force is acting on this, on the car? The only real force there is gravity. So gravity exists, and there's a component of gravity, and I don't know how many colors I can do with this. There's a component of gravity that's acting against the road. So the faster I go, the greater the outward force, v squared over r. I will want to go off the road, off the top of the curve. That is being balanced by gravity. So the faster I go, the steeper that slope needs to be curved. By the way, what else keeps me on the road from sliding off?
Coriolis?
No, on an actual road, it's force. Because what does this force do? It makes my car feel heavier. Right? There's part of the outward centrifugal force pushing onto the road, which is making your car heavier. But there is resistance because of friction that's based on mass, right? Force is a mass times acceleration. So I've got additional mass to keep me on the road. If I had no friction, the car would go flying off the road because there's nothing to stop it from doing so. I don't have enough gravity to do that. The point is, if I go faster and faster, I could slope the road until I'm straight up and down and I go around in a circle. You ever seen those motorcycles in cages? They can do loops this way. You have enough outward force and resistance. If you had no friction, the motorcycles would slip off. But you're going so fast, you're creating enough friction that that balances the gravitational force trying to pull you down. So if I'm going too fast for this in this car, I don't make the curve. And that's exactly what's going on with the pressure gradient force. Okay? Does that make some sense to you?
Mm-hmm.
Then the last problem is...
That is the last problem.
Yeah, no, that's because you're one per.
Oh, that one, yeah.
This one. So it says two ships pass close to a fixed weather ship within a few minutes of one another. The first ship was steaming eastward, so that gives you a velocity. The second gives you a northward, that's your velocity. During the 3-hour period, the ships were in the vicinity. The first recorded a pressure rise of 3 millibars, while the second recorded no pressure at all. During the same 3-hour period, the pressure rose 3 millibars at the location of the weather ship. So in other words, what you have to say is that this here is this. Because it is the local derivative. It's a fixed point. dP dt is different for each ship. right? That's what these are. During the 3-hour period, the ships were in the vicinity of the first recorded pressure rise. That is the pressure change on that ship. It's a parcel. That's the parcel moving. That's what it experiences. So in all of these, when you look at the equation motion, here is the way that you break up your total derivative. Go.
Boom.
This is how you do a total derivative. And what are you given? What do you know, according to what we just said? We know this. We know this. We've been given this. We're solving for dpdx. V for this first ship is 0, and there's no, the ships are not moving up and down, which is good. So all you do is, this is an algebraic problem at this point. The total derivative is definitely calculus, but the work is algebraic. Then we do the same thing for ship 2. For ship 2 over here, the only difference is the u term goes away, this goes, and dp dt on that second ship is 0, which is going to give you some idea. It must mean that the gradient is fully in the x or in the y direction, which is what, if you reason this out and draw some pictures. So Jim, I'm assuming you drew some pictures.
Of course. Oh, yeah.
So,
I can't do problems without pictures.
and you know, that's the way it should be.
That's how I was schooled.
You should not be able to do problems without pictures, because your brain has to figure out what's going on. And I think that's what happens with some of you guys, especially when you're new, is you're trying to reason it out in your head. You need to reason it out external to your brain. Put it on a piece of paper. So we get the same thing. Assume air parcel is a ship, which is exactly right. And you get all this. Once you get the pressure gradient force, you know where you're at. Here you're using the density. Did they give you the density?
No.
I kind of cheated, and no, they didn't, but I kind of cheated and
Use 1.25?
yeah.
Yeah. They didn't give you any clue to what you were supposed to use, so I just used the 1.25 as well.
I think that's a reasonable thing to say. Because, you know, you could talk about heights. That height is why you have gravity. Obviously, you've got weather ships, so you could be measuring temperatures. You know the pressure, so you would know the density, whatever. And that's how you do that. So these problems are really good. I like this one because it's a total derivative. And so I would say, so you got the same answer, Nick?
Yep.
19.9 meters per second. Mike, were you able to reason out stuff like this?
Yeah, I was way off.
Do you understand what's going on here?
Yeah.
Okay. So that is that. Now let me get out my notebook. Give me a second here to do this. And we want to do something like this. Okay, so I'm going to go to a total different I think I've already done the derivatives of the continuity equation, didn't we? We talked about the different terms. Did I do this? I hate to do this. I'm not sure if I did this. So let's do this together because I like this one. So I'm going to show an identity. Okay, so this is what we call an identity. It's a vector identity. And let's just kind of prove that this identity is true. First of all, what is the left side? What is this?
Oh,
What is this? Guys, this is a simple question. What is this?
Del operator.
That's what I want. Del operator. Okay, what is the del operator? It is d dx plus d dy plus
D
d
dz.
dz. But because it's a vector, I need to put I hat, j hat, k hat, right? What is this?
it's a vector.
It's a vector. It's a
It's a
velocity.
gradient. It's a gradient. Oh,
No,
no.
it's a gradient. It's just a scalar.
Scalar.
Scalar is, density is a scalar. It's just a quantity, right?
Right.
So it's a scalar times,
A
just
vector.
multiplying a scalar times a vector.
Okay.
So I don't even need to think much about this scalar. We'll call this, so what I will do is I will call the scalar s times the vector. So it's going to be times s u I plus s v j plus s w k. Is that, do you agree with that? That's just a scalar. Now, is it easier for you to keep in row? It might be. Does that make sense? That's the left side. Now, this is a simple dot product of two vectors. That's what this is, right? That's what the left side of this equation is. It is a dot product of two vectors. So I know how to take dot products. And it will be d rho u dx plus d rho v dy plus d rho w dz. Okay, what's the next step?
Vector out row.
Can I knew that's what you were gonna, somebody was gonna say. Can I just factor out rho?
They're partial
No, you
derivatives.
can't.
Why not?
Because they're dependent on, yeah.
Can't the density change in the x direction?
Yes.
Mhm.
So if this is just a derivative, right? So I can take the chain rule of the derivative. So that's just going to be rho times du dx. Now, for simplicity, it's going to be times du times d rho dx. But I'm going to write that over here, okay? That's just the product rule. Hey, James, how are you doing today? James, are you there?
Typing it.
Did he say anything?
Yeah, he typed it.
Oh, what did he say?
He's doing
Apparently
okay.
Ned is having issues.
Oh, okay. Hey, Jim, were you able to send James the notes?
Yes.
I feel bad, but I wasn't about to redo a complete lecture on a virtual class. Here we go. So does that make sense?
Mm.
Yep.
But do you agree that I would do that with each of the variables?
Yep.
So what I'm really doing is I'm just going to group it this way. Does that make sense to you that I would group it this way?
Mm-hmm.
Because this is just del operating on a vector. So in other words, this is this. And this is this. I probably could have done it better if it was maybe orange. Right? You get the idea? That's that. That's that. Make sense?
Mm-hmm.
Can I erase this? Does everybody see that identity? All I did was expand out simple rules of what vectors are and what the del operator is. So I just expanded this out. Now, why is that important? I'm going to erase all of this. I wish I could just erase everything within a box. Okay? And now I want to say, all right, guys, what is this? What is this statement here? What is this? I always forget. What is this? Now you should know what this is.
Divergence of
Times what?
times density.
Which is basically what? Mass divergence,
Nice divergence. Okay.
right? And then what's this?
First term is divergent. Wait a minute.
Well, the first term, right, this is mass divergence. What is this term? And this is where you always, class, you always forget what this means. Velocity times a gradient is what?
Vorticity.
You did that last week too.
Advection.
It's advection.
Convection.
Vorticity is a cross product, del cross V. So this is your advection. Velocity times a gradient is advection. Okay, so I have divergence and advection of mass. Okay, so let's take this. Remember, when I expand the total derivative, I get the local derivative plus this, and then this is equal to 0. Because I'm saying if I follow a parcel, what kind of a parcel is it?
Ranging.
It's a Vegas parcel. Can that parcel lose mass? What's in the parcel is in the parcel. Therefore, the total change of the mass in time has to be 0. That's following a parcel. So I look at all this and I'm like, okay, there's this equation. I'm taking this equation and I'm substituting this expanded term. So what we can say is this. This plus that is the total derivative oh, here, I did this wrong. Guys, I'm sorry. I'm just going to admit this is a mistake here. That's the total derivative of density.
Those two components.
Yes, because it's the velocity times the gradient of this. So those two things are the total derivative. So I take in here and I go, all right, this is actually d rho dt plus rho and now I'm going to rearrange the terms. Is this term 0?
Is that term 0?
What kind of a parcel is this? I just asked you this. What kind of a parcel is this? It's a
Biggest
Vegas
parcel.
plot.
No
Can the density change of a parcel?
0.
Think about it. Can the mass change of the parcel?
No.
Can the volume change?
Yes.
So can the density change?
Mm-hmm.
Yes.
What causes the change in density?
Pressure.
Pressure. And doesn't this change when density, pressure changes and the
Yes.
temperature changes?
Ideal gas.
Okay. So air can compress. Do you know a fluid that doesn't change the density based on pressure? Did you know that water is incompressible?
I guess I know that.
So if I have water moving around, water is non-divergent because the left term will be 0, the right term must be 0. So when water's flowing, it's not changing its density under whatever pressure you've got, therefore it's non-divergent. However, what could cause it to diverge? Changing the temperature. When you heat water, it expands. Just like when you heat a gas, it expands. The only difference is a gas is also compressible. So I'm going to look up something here. Called the Boussinesq's approximation. Let's see what Wikipedia has to say. In fluid dynamics, the Boussinesq approximation is used in the field of buoyancy-driven flow, also known as natural convection. It ignores density differences except where it appears multiplied by g. The essence of the Boussinesq approximation is the difference in inertia is negligible, but gravity is sufficiently strong to make the specific weight appreciably different between two fluids. So let's take a look at this equation. Have you seen this?
No.
So that first thing that we drew in your notes is the continuity equation. If density variations are ignored, this reduces to the del operating on a vector, the velocity vector. That's the divergence, which means the divergence is 0, which means it's non-divergent. The general expression for the conservation of momentum is this. So there's body forces like pressure gradient, here's Coriolis force, gravity, something like this. And then this is a viscosity term. So now we're getting into the Navier-Stokes equations, getting way beyond where we're going to go in this class. However, it's important to realize that there is a thermal expansion. The Boussinesq approximation states that the density variation is only important in the buoyancy term. So changes in density are only when multiplied by gravity. Well, when do you see density multiplied by gravity? What equation do we see all the time?
Hydrostatic.
The hydrostatic equation. And therefore, density changes become super important. So if you ever see that, and this would be something that I'd want you to put into your notes, talk a little bit about that. All right, now let's go to, so does anybody have any question on this? So this term being equal to 0 is the continuity, mass continuity equation. And then we start understanding how a parcel changes its density based on pressure changes, but the mass doesn't change. So mass continuity is different than density because density relates to volume. Okay, does that make some sense to you? Let us do this. Let us go to here, and I'm going to start drawing some stuff, and you tell me what this is. What's that? Here, you guys got to give me a second because I need more coffee, just because I need more coffee. Hello, I'm back. What is that?
First law with the ideal gas law.
Right, first law of thermodynamics, right? That's just, it's a work term, heating term, and temperature. So heat in, dq, equals work expansion plus a change in temperature. All right, now I'm going to do this. What have I done?
Sorcery.
I have done sorcery. What did I just do here? This is pretty straightforward.
Define it over time.
Which means I did what? I took the, basically what I'm saying is I took the time derivative. And anytime you have a time derivative, what are we now calling this? When you take the time derivative, what's the name that we give to something with the time derivative? Is that just a rate?
Oh, okay.
No, that's all it is we're making it a rate. The left term goes to this.
Is that
So what
H
am I?
dot?
H dot, right? So that's, when you see the dot, remember we said that makes it a rate. A rate of what? What's H do you think stands for? Would you agree that's heating?
Heating. The change of heating over time.
Right? Equals Cp dt minus alpha Vp dt. Now, what I want to solve for is I want to solve for dt. So if I put dt dt on the left side, what would be on the right side?
Minus h dot over CP.
Let's think of it this way. Rather than the minus sign, let's keep the dt over there and just bring this over there so everything's positive.
Okay.
Can I do that?
Why not? You're the teacher.
So this will be h dot
Dot
over
CP
cp, and then what would this one be?
minus alpha. Oh. Okay.
What else do I need?
You need to divide it by
Also-
CP.
But alpha equals RT over P. Right? So I'm going to plug that into here. And what do I get? dt dt equals h dot over cp plus what? I have r over cp. Anybody know what letter that is?
Oh. Kappa.
Remember it was kappa? Remember r over cp equals this kappa? And then I will have t over p times dp dt. But what's dp dt? What's dp dt? That's omega. So
Oh yeah.
this is a what kind of derivative?
Total.
Total.
Therefore, I'm following a parcel. So how does the temperature change following a parcel? A couple things can happen to it. I can heat, this is called diabatic heating. Right? What is this then? Isn't that adiabatic term? Because it's changing the pressure over time, which means the temperature would change because adiabatic and diabatic terms. Now, I could have taken a different equation in here. What equation I could have done is I could have used another form of the first law of thermodynamics. I could have used this term. Remember that? So I could have used an alternative form. And I would have gotten, if I took the time derivative of this guy, I'm trying to figure out, I wrote something in here, and I think the book does this. And I'm just trying to figure out why I would do this. So I'm just going to go dq dt equals cv dt dt plus p d alpha dt. So this deals, what would you call this term?
Ugh.
What is this expressing? Isn't that an expansion? That's, I mean, it's still adiabatic, right? It's still,
It's adiabatic
there's an expansion. Just using something different here. And so in order to expand something, what needs to happen? You're basically saying I'm adding heat to cause this expansion, which is work, plus the heating term.
So the first term is the heating term?
Mm-hmm. I have really horrible notes. Okay. This is the worst notes that I have in class. I don't think I usually get to this point. What I'd like to do is I'd like to take I'd like to go back to this equation, okay? So what I want to do here is I'm going to take this equation and I'm going to go over to this. And I want to expand this out. So I'm going to get the heating term is equal to Cp Does that make sense?
It's alpha omega.
Mm-hmm. What would I need to do then if I solve for omega?
Drag the first term to the other side. R.
Okay. Here. And what I have here is an expression for omega. Now I want you to think about this. Omega is a vertical velocity in the atmosphere. Well, what causes that vertical velocity? Changes in temperature that come about from heating and the advection of temperature. Are you now seeing that vertical motions in the atmosphere are related to the temperature? We had used vertical motions as accelerations dealing with the hydrostatic, which says what? What does the hydrostatic say? It says dp dz equals minus rho g. What are these? This is what? This is gravity. This is an upward vertical pressure gradient. Okay, so let's see if you remember this. This is a while back. What is the hydrostatic really? What is the hydrostatic really? So I hope at this point in our class, you know that the hydrostatic is a vertical balance of two forces, pressure gradient force and gravity. But what is the hydrostatic really? How are you going to answer that question?
It expresses the change in pressure with the change in height is equal to the density of air times the gravity constant.
Let me give you a hint.
Okay.
Jim, you're wrong because you're only telling me what is. And that's not correct. If I said I want to go into meteorology, what do most people think meteorology is?
Forecasting.
Forecasting. What's a forecast?
A prediction of what the weather will be.
Right, which means it is needing a what?
I'm sorry, say again.
What does it need? A prediction needs a what? Like in an equation. What do you call an equation that predicts?
A model.
Models do that, but what do you call an equation that predicts? What's the
Prognostic.
Remember I said, Jim, you were only telling me what is. What do you
Is.
call an equation that tells me what is?
Static.
No, not static.
Dynamic.
Dynamic means it's changing. Static means it's not. What do you call an equation that tells me what is?
A state equation.
Go to the doctor.
Diagnostic.
An equation that tells me what is diagnostic.
Okay.
What do you call an equation that forecasts?
Prognostic.
That's prognostic. In order to have a prognostication, what do I need to have present in an equation? Here. In order to be prognostication, don't I need a time derivative?
No. Okay.
Right? I need a time derivative. That's a prognosis. Do you see the hydrostatic having a time derivative?
No.
No.
Right? So turn to page 291. Look at equation, or look at section 7.3.2. What does it say in 7.3.2? What's equation 735?
Newton's second law of vertical motion.
Right, it's Newton's second law. And what is the left-hand side of the equation? Isn't that the change in the vertical velocity?
Yeah.
Which means it's a vertical acceleration. A vertical acceleration means that the air up and down is changing over time. It's a time derivative. And what is it equal to? It equals to the pressure gradient force and gravity, and the Coriolis force and friction. So what's the hydrostatic really?
Vertical motion.
No.
What is it really?
It's really equation 735, but what have you done to equation 735? Okay, I'll give you the answer. The hydrostatic is really the scaled version of the vertical momentum equation. Right? Because if I scale this thing, which is what it says in the paragraph below, these two forces, the vertical pressure gradient and gravity, are so big. Everything else is really small comparison, right? The magnitude of gravity is 10 meters per second squared. The magnitude of the Coriolis force is 10 to the minus fourth. That's 10,000 times smaller. The vertical Coriolis force for atmospheric motions is insignificant. I scale that out. What about friction? Vertical. Small. But if the pressure gradient force and gravity are so strong in balance, how does the vertical momentum, vertical motion, how does it accelerate? The answer is it doesn't accelerate. In hydrostatic balance, the forces are balanced, there's no acceleration, which means the vertical motion field of the atmosphere, if it were hydrostatic, never changes. When would that not be true? When does the pressure gradient force and gravity not balance?
You have rising motion.
No.
Convection.
In thunderstorms, convection.
Convection.
Because it's unstable, right? That temperature difference it offsets the hydrostatic. But in hydrostatic, do you have vertical motion?
No.
Yes.
Technically.
No, you do. But based on hydrostatic, what can you tell me about the vertical motion? It doesn't change. Is that true of the atmosphere? Does the vertical motion of the atmosphere change? Yeah. Can I figure out what that change is using the vertical motion momentum equation? Okay, I think I'm not making myself clear. Two forces are balanced. What's the net force?
Zero.
If the net force is zero, does it change over time? No.
No.
Do you understand that the vertical motion in the atmosphere does change? How do I figure out what that change is if I said that the net force is zero? If pressure gradient and gravity are so strongly balanced, how can I talk about changes in the vertical motion field? And the answer is, in hydrostatic balance, I can't. And the atmosphere is hydrostatic almost always. Now, In geostrophic balance, it's pretty easy to talk about changes in the field. Why? Because when I have any deviation from geostrophic, the atmosphere adjusts. I can calculate that change. It's the ageostrophic acceleration, like we talked about last week. That's easy. I can do time derivatives of that. I know that. But in the vertical, I don't have a time derivative in my equation. Okay, 7.3.3. Jim, would you please read that, the evolution?
The evolution of weather systems is governed not only by dynamical processes as embodied in Newton's second law, but also in thermodynamic processes as represented in the first law of thermodynamics. In its simplest form, the first law is a prognostic equation relating to the time rate of change temperature of an air parcel as it moves through the atmosphere. These changes in temperature affect the thickness pattern, which together with appropriate boundary condition determines the distribution of geopotential on pressure surfaces. Thus, if the horizontal temperature gradient changes in response to diabatic heating, the distribution of the horizontal pressure gradient force in the horizontal equation of motion will change as well. First
right.
law.
So what you're saying is that when I've got heating differences, it becomes pretty simple to realize that my pressure field is going to change. Temperature gradients set up pressure gradients, and the atmosphere changes. And those are calculatable. Okay? Now, the next couple of paragraphs, the equations are the thermodynamic energy equation. That's what this is. This thing that you see on your screen is called the thermodynamic energy equation. And the only difference between your book is that I'm using H, and what do they use in the book?
J.
J. And they say J is diabatic heating, and they multiply through by dt, right? So pretty much the same thing. And they tell you a little bit about this underneath 7.36. Take a look. Underneath that, there's a paragraph that talks a little bit about traditional values, about how much this actually is. The next one talks about the diabatic heat sources. So it says, the second term says you've got absorption of solar radiation, OLR, latent heat release in the upper atmosphere, heat absorbed or liberated in chemical and photochemical reactions. That's way up there, way beyond where we typically are forecasting. It is customary to include as part of the diabatic heating the heat added to or removed from the parcel through the exchange of mass between the parcel and its environment due to unresolved scales of motion such as convective plumes. So that's when they say, okay, the parcel doesn't really exist, right? The Vegas box is a hypothetical box, not a real box. It says, throughout most of the troposphere, there tends to be a considerable amount of cancellation between the various radiative terms so that the net radiative heating rates are less than 1 degree Celsius per day. In other words, the change of temperature in a parcel is really pretty small because I've got energy coming in and energy going out, which tends to balance each other out. So you're not really looking at huge temperature changes due to the heating term. Latent heat release tends to be concentrated in small regions, which may be locally comparable in magnitude to the adiabatic temperature changes discussed earlier. So now they're saying, okay, so there's heating, and that heating is comparable to the adiabatic temperature changes. And what are they saying in this scenario? Well, they're saying if I scaled the thermodynamic energy equation, sometimes latent heat is big term. Think thunderstorms, right? Instead of being 10 degrees Celsius per kilometer, I'm now 6 degrees Celsius per kilometer. I've cut the dry adiabatic lapse rate almost in half. That's 50%. That is not something that can be scaled out. It is significant. However, throughout most of the troposphere, the sum of the diabatic heating terms is much smaller than the adiabatic temperature change. So outside of those kind of events, for the most part, it's smaller. Using the chain rule, that equation may be expanded to obtain the Eulerian or local time rate of change, which is what we've talked about. So look at equation 7.37. The first term on the right-hand side may be recognized as the horizontal advection term. The second term is the combined effective adiabatic compression and vertical advection, right? And then there's you can, if you want to do that problem, that would be a really great problem to go through. In a stably stratified atmosphere, dTdP must be less than the adiabatic lapse rate, blah, blah, blah. It follows that sinking always favors local warming and vice versa in a stable atmosphere. Again, if the lapse rate were greater than 10 degrees Celsius per kilometer, that would be different. But you have to understand, sinking air is always leading to warming. What would rising air do?
Cool.
Cooling. Side note, just for a second, here is an inversion that we see in the atmosphere. Let's say we see that at 12Z. If later on we see this as a lapse rate, what has happened? The temperatures have cooled.
You've got sinking air.
Oh, they're right.
You got rising air because the
Rising.
energy transfers to the parcel. Okay.
So if you ever see a cap in the morning on a sounding, if it goes away later, there's only one reason that cap went away. It's not advection. That's very small. It's rising air. Air has been rising. That's what we talked about in 1115 as a convective battery. The fact that we're always trying to break through that cap. Okay? If the motion is, in the next paragraph, if the motion is adiabatic, in other words, the heating term is 0, and the atmosphere is stably stratified, air parcels will conserve potential temperatures as they move along their three-dimensional trajectories, carrying the potential surfaces or isentropes with them. In other words, the parcel maintains its potential temperature theta, which means air travels on isentropic surfaces. Which requires the slope of the three-dimensional trajectories be identical to the slope of the local isentropes. So when we talk about warm advection, we're actually looking at isentropic lift. That's where this comes from. You've heard us use that term, isentropic upglide, because you have to conserve potential temperature. Throughout most of the extratropical troposphere, the trajectories typically slope about half. So what that does is I want you to go look at something. Oh, where's a picture? Oh, damn. You have your old book?
Yes.
They have a picture of this. Here's your isentropes. Okay, let's say they're sloping this way. If the flow is going to be parallel, the flow would actually go that way. But what does that last paragraph say? Throughout most of the extratropical troposphere, This trajectories typically slope about half as steeply, which means they're flowing like this way. Instead of being this way, they're maybe this way. So what is this? What does this actual flow, and if these are isentropic surfaces, what does that tell me? What am I illustrating with this picture?
Heat advection.
What?
Type of heat advection.
Right? That is advection. I'm actually advecting air, or advecting temperature. Or I even like the way Mike said it. I'm advecting potential temperature, which is heat advection. I think that's a good thought. And when we go into mesoscale, we can get into convective instability, and we can get into slantwise convection, and we can talk about how air is going to become unstable. It's pretty cool. It's all based on things like this. So we'll come back to this, I think, maybe if we have time on Thursday, but I want to continue on. Hence, the horizontal advection term tends to dominate, and the motion has the effect of flattening out the isentropes. In time, the isentropic surfaces would become completely flat if it were not for what? The meridional heating gradient, which is continually tending to lift them at high latitudes and depress them at low latitudes.
Okay.
So in other words, because of the meridional temperature gradient of the spherical Earth, we continue to do this. So the motion of the atmosphere is to make the isentropic surfaces parallel, and that keeps getting tilted up. By the way, here's a question for you. Which side of this diagram, and this is going to take some thought, is cold? Remember, if this is, let's say, 300, and this is 305, and that's 310, then what's the potential temperature here? 300. What would the potential temperature here be? 295 maybe?
Mm-hmm.
So this side is the warm side. Isentropic surfaces get pushed up on the poles and get pulled down at the equator. It's kind of different, right? If these were isotherms, you'd say differently, but that's not what we were looking at. So this is warm air is pushing this way. It's warm advection. I just thought that's kind of cool. Okay, so you can read the rest of this, and I think that's fine. Let's go to the top of page 293 on the right side. The vertical motion field cannot be predicted on the basis of Newton's second law. It can only be inferred from the horizontal wind field, which is the continuity equation. So what we're saying is, because of hydrostatic, we cannot use Newton's second law to do a prognostication of the vertical wind field. It's got to be a result of convergence, divergence. Those things that we did in class with the little DNA diagram talks about vertical motion based on convergence. We're summing up convergence, and we get rising air. But here's the problem with this. In the atmosphere, when the air is speed divergent, speeding up, it tends to be confluent. And since confluence is opposite divergence, I've got two big terms, and I'm looking at the difference to determine the vertical motion. And that's really hard to do. I cannot do that. And then it talks about this next one, which we've done with continuity. We did this, so go back and look at this again. Here, top of page 294. Integrating the continuity equation, Margulis pressure tendency equation. All of this stuff goes on. We've talked a little bit about it. Here we're talking about gravity waves, and then we just kind of go on past it. So we're gonna jump past this. I think you can read this on alone. Solution of the primitive equations are basically saying we've got prime. Look at page 296. Prognostic versus diagnostic. So there's a few things that I want to go through with on Thursday, but there's one last thing that I did want to talk about, and that is this. I want to go to the quasi-geostrophic omega equation. Let's see what Wikipedia has to say. You may, and we're going to call it quasi-geostrophic. It says the omega equation is the culminating result in synoptic scale meteorology. It's a differential equation. So to actually do this, we need differential equations. The underlying concept is more general, however, can be applied to the Boussinesq fluid equation system. Concept. So go ahead, Nick, would you read this starting here?
Sure. Vertical wind is crucial to weather and storms of all types. Even slow, broad updrafts can create convective instability or bring air to its lifted condensation level, creating stratiform cloud decks. Unfortunately, predicting vertical motion directly is difficult. For synoptic scales in Earth's broad and shallow troposphere, the vertical component of Newton's law of motion is sacrificed in meteorology's primitive equations by accepting the hydrostatic approximation.
So in other words, because we accept the hydrostatic, we are taking Newton's second law, which is force equals mass times acceleration. We're saying that the net force is zero, therefore there's no acceleration. The primitive equations, primitive means foundational. The foundational equations of the atmosphere, first law of thermodynamics, ideal gas law, the thermodynamic energy equation, mass continuity, and Newton's laws of motion. So in fact, if you go ahead and open this in a new window, continuity, conservation, momentum, thermal energy equation. Right? Those are the basic equations that how we do modeling. That's how we figure stuff out. Okay, keep going.
Instead, vertical velocity must be solved through its link to horizontal laws of motion via the mass continuity equation. But this presents further difficulties because horizontal winds are mostly geostrophic to a good approximation. Geostrophic winds merely circulate horizontally and do not significantly converge or diverge in the horizontal to provide the needed mass link or the needed link to mass continuity and thus vertical motion.
Geostrophic wind is non-divergent. So the only way that you get vertical motions is if you have convergence or divergence, which is ageostrophic. Ageostrophic winds are going to result in vertical motions. Look at the next thing there. Go ahead, keep reading, buddy.
The key insight embodied by the quasi-geostrophic omega equation is that the thermal wind balance, i.e. the combination of hydrostatic and geostrophic force balances above, holds throughout time, even though the horizontal transport of momentum and heat by geostrophic winds will often tend to destroy the balance. Logically, then, a small non-geostrophic component of the wind, one that is divergent and thus connected to vertical motion, must be acting as a secondary circulation to maintain balance of the geostrophic primary circulation. The quasi-geostrophic omega is the hypothetical vertical motion whose adiabatic cooling or warming effect, based on the atmosphere's static stability, would prevent thermal wind imbalance from going with time by countering the balance destroying or imbalance creating effects of advection. Strictly speaking, QG theory approximates both the advected momentum and the advecting velocity as given by the geostrophic wind.
Okay. It says, in summary, one may consider the vertical velocity that results from solving the omega equation needed to maintain geostrophy and hydrostasy, geostrophic and hydrostatic balance, in the face of the advection of the geostrophic wind. This is coming from Holton. This is the big book on dynamics. I wish I could teach that course to all of you. Maybe if you guys all took up a petition next year, we could do that course. That'd be really fun. Look at the equation. Let's just take a look at a couple of terms that are listed in here. And I'll show you why I can't teach you this in this course. F, Coriolis, I know that. Omega, vertical motion, I know that. Change in pressure, I know that. Sigma is static stability, I know what that is. Geostrophic wind, gradients, vorticity. I know all these things. The only thing that's weird that I don't know is this term. This is the del operator squared. That's called a Laplacian. It's the Laplacian operator. And that becomes a little bit more difficult to try to explain. So this becomes really, really hard, right, to teach this one. And then they do a derivation. And there's all sorts of funky stuff in here. Where absolute vorticity, right? You could go through here and look at this. Oh, the thermodynamic energy equation written as kappa. Oh, kappa is the relationship of CP over R. And then we do all this stuff, right? This is a lot of mathematics. Doable takes a long time. Expanding the final tilting term, right? We talk about tilting. Then we take the Laplacian. Oh, I don't know this. Oh, using the Jacobian. Oh, crap. Whoops, didn't mean to do that. I don't want that. I don't want any of this mathematics. There comes a point where I can't teach you all the mathematics until you get there. This is way past calc and differential equations. And then we go on and we're like, okay, wait a second. So what the hell am I supposed to do with all this? So what I'm going to do in here is I'm going to put in the word Doswell. And when I go to Doswell, I'm going to find something here. Vorticity, advection, and vertical motion. Technical discussion of the omega equation. Blah, 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 blah. Talks about things called Q vectors. And then we go to the non-technical discussion of the omega equation. And what we say is we have two terms in the omega equation. So what I want you to know is this. The the change in the vertical motion is equal to thermal advection and dCVA. That's what we are going to state on this. Thermal advection means warm air advection means rising air. We have taught in forecasting in all my classes, warm air advection implies rising air. Well, that concept is the quasi-geostrophic omega equation. Qualitatively, not quantitatively. I'm not going to make you do that. You're coming out of COD without a quantitative understanding of the quasi-geostrophic omega equation. But you should have a qualitative one. Warm air advection implies rising air. Mike, you just said we had that advection of warm air. The air is going to go up at about half the isentropes. That's advection of warm air. Air is ascending. That's what it means. What does cold air advection mean? Cold advection means sinking air. Now, Jim, and I think this is where you got confused a little bit earlier. When the air sinks at the ground, what will the temperature do? At the surface, the temperature should go up, right? Because it's being compressed.
Right.
But really, what you're taking is air of higher theta values and advecting or convecting it downward. That's why it's warming. It's actually vertical advection. Because in a stably stratified atmosphere, the heat in the air is actually higher the higher up you go. So sinking air is actually warm advection. Warm vertical advection or convection. Now, the other thing here, do you remember, Jacob, do you remember what dCVA stands for?
Not off the top of my head.
Vorticity.
Differential cyclonic vorticity advection.
Ah.
So here is what Chuck says to do. Look at figure 1. I have a vortmax within height contours. So over here, right over there, do you understand that the amount of vorticity is advecting toward me? We used to say positive vorticity advection. Positive vorticity is implying cyclonic. So now we say cyclonic vorticity advection. And that's what that means. The trough, in a very real sense, is defined as the blob of enhanced vorticity. Right? I mean, if you've taken forecasting from me, we always go, there's the vortmax, there's the shortwave. Well, this is why. Okay, now consider a parcel entering from behind the trough. So now I have a parcel going into the trough. Okay, that's what's going on there. And what that means is it has some vorticity as it enters the trough. Along its trajectory, it's going to spin faster. To stay in equilibrium with its environment, it must increase its vorticity. In other words, that parcel has to spin faster in the trough. How does this do so? Well, the change in vorticity over time is the ice skater and other stuff. So to spin faster, changing its vorticity. I'm going to assume the other stuff is negligible. The only way an air parcel can increase its vorticity is to do what other skaters do to increase theirs. The air must converge, so that the conservation of angular momentum requires the spin to increase. By this reasoning, parcels entering the backside of the trough in a region of anticyclonic vorticity advection are having to converge. By the same argument, the region of cyclonic vorticity advection on the other side of the trough parcels are diverging. This has nothing to say about the level where all this is happening. So here, PVA equals upward vertical motions depends on this. Parcels are moving faster than the troughs. Is that always the case? No. Parcels seek to maintain vorticity values in equilibrium with their surroundings. Kind of. The level where vorticity advection is being evaluated is above the LND, the level of non-divergence, which is 500 millibars. The only kind of diversion of vertical motion is vorticity advection, and that's not true. Thermal advection is the most important thing. So what I need you to do is I need you to read the rest of this stuff. So I think if you do that, if you just go to flame.org, you should be able to get this stuff. But what it's saying is that in order to get this vorticity to spin up, it needs to be stretched. Right? So we get a stretching in there. And the way that you're going to do this is if there's going to be advection. So basically what we are saying is this, and I'm going to finish it with this last thing. If all those assumptions are met, what that basically says is this. Air rises ahead of the trough. And behind the trough, what does the air do? It sinks. Hello? Was that somebody in your, oh. God, that scared me. I thought somebody was in my house. Was that you, Jacob?
Haunted.
That's what the quasi-geostrophic omega equation is. That's what it tells me. Air rises, air sinks behind the shortwave. So when you're doing your final stuff with your notebook, make sure you get that Chuck Doswell stuff in there because that's really the important QG. It'll talk about being able to spin differently, and it's complex, but that's the basic idea. And so his 5 assumptions are going to be good. So when you're doing that final question, make sure that you've gotten this information in there from Chuck Doswell. Do you have any questions on that? Are you okay with that?
Mm-hmm.
Get that information. And the qualitative form is what I'm doing. But that allows me to understand how vertical motions are in the atmosphere. So on Thursday, we have baroclinity, thermal wind, shear. We can finish all this stuff pretty straightforward. And then we'll do a little bit of general circulation stuff. So we should be able to finish that no problem.
I just put the link to that in there.
Thank you, Nick.
Mm-hmm.
Okay, anybody have a question? Go ahead and grab that really quickly, and I'm going to end this session. So we'll see you guys on Thursday.
Right. See you Thursday.
See ya. Bye, guys.
See you.